Good morning and welcome you all to this session of the course. Now, next is this diffuser. Now, I come to the next part, that is the second component, diffuser. Now, what is diffuser? That is same as that of your centrifugal pump diffuser. Now, we know that impeller and diffuser are the two important parts. This is impeller. This is impeller. Now, what happens? Energy is added to the impeller. So, when air comes out of the impeller, what happens? The air acquires energy by the momentum transfer of angular momentum by the rotating action of the blade, which we have done. How to find out the increase in how to find out the work input to this. Now, what happens when it comes out of the impeller tip? The energy is stored in the form of both kinetic energy, velocity of the fluid, and the static pressure. The impeller passages are made diverging, so that the pressure will increase in the direction of the flow. But we want finally from the outlet of the compressor, that means if you see this diagram, it will be better, that at the outlet of the compressor from here, the delivery, we want air at relatively much low velocity, but at high pressure. Why? This is because the practical use of these compressors are with the engines or with the plants, gas turbine plants, turbojet, turbopop, turbofan engines, where this air is used in a combustion chamber to burn the fuel, and when the fuel is burned, a high temperature is generated, or a high temperature, the air is heated to a high temperature by the energy generated because of the burning. So, to make the burning more efficiently, what is required is that a high pressure air at high temperature and high pressure air, but at very small velocity, as low as possible. Sometimes it is unavoidable for different reasons that you will know afterwards if you read the jet engines or the gas turbines in more detail, but as far as it should be avoidable, because a high velocity in the combustion chamber for burning fuel causes several problems like combustion instabilities. Combustion cannot be made so efficient. So, to make the combustion more efficient, it is required that a relatively low velocity but high pressure air. Okay. So, for that we want that the total energy of the air at the outlet should be mostly in the form of static pressure, or you can tell the stagnation or total temperature at the outlet, which is the index of the work given to the fluid, should come in the form of only the static temperature or the static pressure, not in the form of kinetic energy. Kinetic energy will be there as required for to maintain the flow. So, therefore, what happens? The excess, that means the kinetic energy which is there, which is undesirable, is then converted to pressure energy or to convert it to higher static pressure in the diffuser. The similar thing which is done in the case of centrifugal pump. So, this diffuser is like this. There are, first of all, there is a veneless space. First of all, there are no vein. So, it is a veneless space where the diffusion takes place partly, and after that there are number of veins which makes the final diffuser. Now, why the number of veins are made? To divide the air stream in several channels to make an effective control of the flow, and at the same time we can get the diffusion, that means a rise in static pressure at the cost of the kinetic energy in a short length, as short as possible. So, because of this, the veins, number of veins are there to direct the flow in different channels. Now, I will come to the veinless space afterwards. Let us first discuss these veins. So, these veins create the passage. So, each and every passage, this is the width of the passage, has a divergent width. The width diverges, which depends upon the shape of the vein. So, veins are curved. So, depending upon the curvature, the widths are made so that the cross sectional area normal to the flow increases, because of which the velocity decreases and pressure increases. The depth which is perpendicular to this plane of the figure, the depth of the diffuser is usually constant in the direction of the flow. This means, that means it has a constant depth. This is the perpendicular to the plane of the figure. Now, before going to explain this, I will tell another criteria, what should be the curvature of the veins, so that the diffusion process, that is the deceleration of the fluid, is efficient without losses. So, that is more important in a diffuser. So, therefore, we must tell something about boundary layer separation. Boundary layer separation. Now, let me tell you something about boundary layer separation. Okay. Now, let me tell you something about boundary layer separation. Now, you see that when a fluid flows, come to the basic principle of fluid mechanics, which probably you have learned in fluid mechanics. Again, it is a recapitulation of the earlier things, that when a fluid flows from one point to another point, or in an average from one section to other section, what is the gradient which makes the flow possible? It is the energy gradient. That means fluid flow from a higher energy to a lower energy. So, therefore, when the fluid flows from a point or a section to another point or section downstream where the pressure increases, then the fluid flows against an adverse pressure gradient. Why? Because fluid element faces a higher pressure at the downstream. That means the direction in which it is flowing, but still the fluid flows because of the energy gradient. Energy at upstream is always higher than that at the downstream. But what happens, you see, that when the fluid flows past a body, let us consider this, a recapitulation. Let us consider the fluid. Now, to understand this, let us consider an external flow. A fluid is flowing past a curved surface, for example. Now, let a fluid enters with uniform velocity. Let us recapitulate what is boundary layer flow. Now, you know that when the fluid flows past a solid surface, at the solid surface, the relative velocity of the fluid with respect to the solid surface, or the velocity of the fluid relative to the solid, is 0. This is purely because of the interaction between solid and the fluid. This is pure interactions between the solid and the fluid. I am not going into details of it. This can be broadly conceived as a consequence of the adhesion between the fluid and the solid and their interfacial process, by which the fluid is not allowed to slip over the solid. That means its velocity relative to solid is 0. That means if the surface is at rest, the fluid velocity will be 0. And what happens? The fluid just above it, in the near vicinity of the solid, is being retarded to a very low velocity, because this happens to the momentum transport in the cross direction. Because of this momentum transport from fluid to fluid, because of the molecular transport, it is at the molecular level, the fluid velocity from 0, if we consider the solid at rest, ultimately attains the free stream velocity. Ultimately attains the free stream velocity. It attains actually asymptotically at any section, but if we consider some 99% of the free stream velocity as the free stream velocity itself, then we can call this as the boundary layer thickness at that section, and this grows like this. That means there is a boundary layer within which the fluid velocity changes from 0 to almost the free stream velocity. So, this retardation of the fluid from its free stream velocity takes place within the boundary layer because of the momentum transport. The fluid is retarded within a layer very close to the solid surface. This is known as boundary layer or the shear layer, which is a function of x. Now, this x at a distance x, I denote the free stream velocity as u infinity x, which may not be the same as the u infinity at the entrance. This is because of what? If the surface imposes a pressure gradient, that means surface due to its curvature may impose a pressure gradient in the potential zone, that is the zone above the boundary layer, where the flow velocity in the transverse direction, for example y, is uniform, and this is known as boundary layer region. So, therefore, this boundary layer is impressed with a pressure gradient which is imposed by the curvature of the surface, that is del p del x. Now, when the pressure at the downstream, let some typical downstream section pressure is d and some typical upstream section pressure is u. When pressure of the downstream is less than pu, by mathematical term we tell that del p del x is less than 0, because this is in the increasing direction of x, in the direction of flow. That means the fluid is flowing with a negative pressure gradient. There, what happens if you consider a fluid element, since this pressure is low and this pressure is high, upstream pressure. So, fluid experiences a net pressure force in the direction of flow. That is why this is known in fluid mechanical term as favorable pressure gradient, favorable pressure gradient. But when due to this curvature the pressure gradient becomes other way, that means the downstream pressure at any typical downstream location is greater than Pu, then by mathematics del P del x is greater than 0. So, a negative pressure gradient means favorable pressure gradient, and this is known as adverse pressure gradient. In this case Pd is more than Pu. So, therefore, the fluid is facing a force, net pressure force in the direction opposite to its flow, that means it opposes the flow. So, this creates an adverse effect. So, that is known as adverse pressure gradient. So, when this type of adverse pressure gradient takes place in case of diffusion, which we are discussing now, where the pressure is increased, this is the static pressure. So, downstream pressure is higher than the upstream pressure, this case prevails. So, fluid faces an adverse pressure gradient, but still the fluid flows because the energy gradient pushes it, energy gradient makes it possible to flow. But what happens for the fluid particles very close to the wall, the kinetic energy is totally consumed, the kinetic energy is destroyed because kinetic energy is ultimately coming to 0, fluid is retarded because of this momentum transport, okay, and this is being manifested by the property fluid viscosity. So, therefore, for the liquid fluid particles close to the surface, kinetic energy falls appreciably so that they cannot surmount the adverse pressure hill. That means the total energy becomes insufficient at the upstream to flow. That means the energy gradient is reversed. Okay, that means the fluid with low kinetic energy near the solid cannot surmount the adverse pressure hill. And then what happens? At some point it happens where the gradient of energy opposes, becomes reversed, and the fluid flows in the opposite way. This is known as flow reversal. If you draw the here the velocity after the flow reversal, here the flow reverses, if you draw the velocity profile, you will see the velocity profile is like this. You understand? So, this part the fluid flows in the opposite direction. This is known as boundary layer separation, and this creates a large number of eddies, recirculatory flows, and by virtue of which the total mechanical energy of the fluid is being curtailed, is being reduced, and what happens? Energy is totally conserved. So, because of this creation of local recirculatory flow in the form of eddies which takes place because of the flow reversals, the boundary layer is detached and all boundary layer assumptions fall there. So, what happens from the practical point of view, that part of the mechanical energy, that means the static pressure, is being converted into intermolecular energy, which from the viewpoint of mechanical energy is a loss, and that is why people tell this is the separation loss. Now, when we give a diverging passage, therefore, now if you consider a diverging passage, the same thing now with this was with the external surface, now you consider a diverging passage. Now, one thing, if the pressure is favorable, then the fluid particle does not have any flow reversals, they always flow. So, therefore, this flow reversals or boundary layer separation takes place whenever the pressure gradient is adverse. This is clear because in favorable pressure gradient, even if the kinetic energy becomes low, the pressure force itself, this is the favorable pressure gradient. This is this case, that there is always a pressure force in the direction. Pressure force will help it to push in the direction of the flow. So, it will never happen with the favorable pressure gradient. This is a very important thing to remember. Now, when the fluid flows in a diverging channel, for example, the streamline may be like this. So, here what happens? The fluid flows that any typical section PD and PU. So, PD is greater than PU. So, here del P del x is, if this is x, del P del x is greater than 0, that means this is an adverse pressure gradient. Here the separation will take place. Whereas, this is the decelerating flow. Decelerating means decelerating. That means its flow velocity is reduced and the pressure is increased. In an accelerating flow, if you consider the flow through a converging duct, that is a nozzle, in case of this is the nozzle flow, this is the streamline. So, therefore, this is the streamline from a far distance, this is parallel. So, in a nozzle flow this is accelerating flow, that is nozzle, where in subsonic flow that I will again discuss afterwards, a converging passage acts as a nozzle or accelerating flow and a diverging passage acts as a decelerating flow. So, that I am not telling now, this will be discussed afterwards in detail, that in a converging passage when the flow is accelerated, which we usually known as nozzle, del P del X is less than 0. That means a downstream pressure is always less than upstream pressure. So, therefore, always there is a force in the direction of the flow to push it. So, therefore, a diverging passage anywhere where you have the diffusion process, that the pressure is increased in the direction of flow, you have to be very careful of the boundary layer separation. Now, this separation is very sensitive with the angle of divergence. If the angle of divergence is more, what happens, that the rate of pressure increase, that is the adverse pressure gradient is more, so that the separation occurs early. So, therefore, angle of divergence, the angle of divergence is very important in a diffuser duct. Divergence is very important and that should be less than equal to 10 degree, 10 to 11 degree. So, angle of divergence should not be made more than 10 degree. So, it is restricted for design of any diverging passage. So, therefore, here also the divergence angle should be restricted at each and every point. Okay? Now, I come to the vaneless space. Now, the divergence angle at the inlet to the diffuser vane should also match with the direction of the velocity, and since the diffuser vanes are static vane, so direction of the velocity means the velocity, absolute velocity, which comes out of the impeller. That direction should match the direction here, otherwise what will happen? Otherwise there will be incident loss at the incident. However, here we cannot say so, because the velocity with which, the direction of the absolute velocity with which the fluid comes out of the impeller is not same to that at which it will enter, because there is a vaneless space. So, therefore, we have to know what the fluid flow, nature of the fluid flow or the flow field in this vaneless space. Now, the first question is that, sir, why I will give a vaneless space? Why not the diffuser vane should be given or should be provided right at the outlet of the impeller tip, so that the fluid which will come out of the impeller will go to the diffuser, but it is not done. Always a vaneless space is provided. This is because of two reasons. First one is that the Mach number of flow is reduced before it enters to the diffuser vanes, and Mach number has to be reduced means that the velocity of flow has to be reduced. So, therefore, it is required that before the fluid enters or impinges or the glides, whatever way you tell, the diffuser vanes, its velocity should be reduced. So, therefore, some space should be given which will act as a diffuser to reduce the velocity. And number two reason is that if we do not give that space, what happens, there will be an excessive circumferential variation of static pressure. If you provide all the diffuser vanes very close to the impeller tip, then there will be an excessive variation of the circumferential stress, which is radially propagated upstream inward to the impeller and creates a vibration, and impeller blades may fail due to this vibrational fatigue. And this vibration is a function of the relative velocity of the fluid and the number of impeller vanes, and it is more dangerous if this frequency of this vibration coincides with the natural frequency of the impeller. And to avoid this, usually the impeller vanes are not multiples of the diffuser vanes. This is one of the reasons. So, therefore, because of reduction of Mach number and the velocity and the circumferential variation of static pressure, there is a vaneless space. Now, vaneless space is a space which having a increasing in cross sectional area, and in the vaneless space, if we want to know the principle, the flow field, then we can write like this: since there is no energy transfer, the VW2, that is the tangential component of velocity at the tip of the impeller into the angular momentum comes out, that is constant. That means VW2 decreases with increase in R. is inversely proportional to R. So, therefore, with the increase in R, the VW2 decrease. There is a decrease in VW2 with the increase in R. Okay. Now, another thing is that if you consider the flow velocity Vf, this also decreases. This is because with the radius for a constant depth, that means depth is constant in the perpendicular to the plane of the figure, the flow area with the increase in R, the flow area increases. So, I write simply the increase in R, because with the increase in R, flow area increases. That means AF increases with the increase in R. So, because of that, this takes place. That means both the tangential velocity component and the flow velocity, okay, both decreases. As a whole, the absolute velocity decreases. So, a diffusion takes place. So, therefore, the Mach number is reduced, but at the same time, this vaneless space has to be designed in such a way that should be in conjunction with the inlet angle of the diffuser vane, so that finally the absolute velocity direction should match the diffuser vane. This is okay. This is almost all about the design of the diffusers. Now, I will come to another thing which I forgot to tell you earlier in this connection regarding this inlet Mach number here. Okay, please wait, I just will show you here. Yes, here I just forgot to tell you that this inlet thing which I have shown you, this velocity, sometimes what happens to reduce the Mach number at the inlet, it is not required here. I told the reduction of Mach number at the inlet. I go back to the earlier discussion that if this is the vane at the impeller tip, this is the impeller vane. So, we know that this is the typical diagram, this is the typical diagram at the inlet. This also I just forgot to tell you, you must know that this is U, this is VR1, this is V1, this already we discussed the impeller vane. Here VR1 is the relative velocity, that is V1, it is U1 minus U1. Now, here what happens to reduce this Mach number, we already discussed earlier that A. Now, A is gamma RT1. How? This is because that this acoustic velocity, which will be again told you afterwards in compressible flow classes, that for a ideal gas, the acoustic speed or sound velocity can be expressed as root over gamma, that is gamma is the ratio of specific heat, R the characteristic gas constant and the temperature T1. So, therefore, this is the expression of Mach number. Now, the VR is sometimes reduced by what do you know? By giving a deflector, and the thing is like this. For the same, I again draw this diagram for the same flow velocity and the same. So, this is the ideal one, this is the ideal one V1, U1 and VR1. So, the dotted one is like this, this will be my final V1. So, what happens? There is certain amount of pre-whirling is given. That means, what is that? I tell you, that is like this, a deflector of this type is given which deflects the flow in this way. Sorry, this will be this. So, this will be my, let this dash now, the ideal one. This is V1 and therefore, this is VR1. So, for the same U1 dash is U1. So, U1 remains same, flow velocity remains same, V1 dash remains same. So, that flow velocity is this component, but the absolute velocity is having some angle. That means, this portion is the, now this portion is now, if you understand well, I am happy, that is the inlet tangential component. That means, instead of having a axial entry which is perpendicular to the direction of tangent, we give an oblique entry by use of a deflector which gives some amount of whirling or tangential component at inlet. But for the same flow velocity, that means to accommodate the same mass flow rate, we have a reduction, that is VR1 is less than VR1 dash. So, sometime a deflector plate is used, but here what we lose, we gain in terms of reducing the Mach number, so that at the impeller tip we may be little sure that Mach number is not supersonic, so that shock losses occur there, but we introduce a whirling component, this is known giving a pre-whirling at the inlet, so that the energy per unit mass or the work done per unit mass is now VW2. As you know, this is the formula, but here now VW1 is not 0. So, if it is 0, it is this. So, therefore, for a given VW1, small VW1 is generated. So, we lose. So, that means at the cost of specific work, we give this pre-whirling. That means the work input to the fluid will be less. That means what we lose is the efficiency of the compressor. That means it requires more energy for a given pressure rise, but the Mach number is reduced. So, this was told, and okay. So, then this diffuser is you know about the diffuser. Now, I come to the losses in centrifugal compressor. Losses in centrifugal compressors. What are the different losses in centrifugal compressors? Now, losses. There are different types of losses in centrifugal compressors. So, they are like this. One is the frictional losses. Frictional losses. Okay. Another is the frictional losses, another is the incident losses, incidence losses, another is the clearance or leakage losses, clearance or leakage losses. Okay. Now, one by one, the frictional losses are typically the friction. Now, the fluid flows through the compressor blade passages, comes in contact of the solid surface and fluid to fluid layer, that is because of viscosity, skin friction is there, that is purely frictional loss. Apart from that, there is a separation loss, boundary layer separation, or there may be losses due to shock. Now, these losses are known totally as frictional losses. Frictional losses mainly comprises the skin friction and the separation loss. Separation loss is very important in compressors because throughout the flow is there with adverse pressure gradient, means that there is always a deceleration of the flow. So, separation loss and the skin friction combines the total pressure losses and the total frictional losses. So, what is this loss first of all? This is loss again, the loss in mechanical energy, which is mostly manifested in terms of the loss in the or the shortfall in the static pressure of the compressor at the outlet. So, frictional losses is because of the friction, the skin friction and the boundary layer separation because of the decelerating. Incident losses are losses because of the fact that when the flow velocity while flowing through the vein does not follow the vein angles, especially at incidence to the vein, if the flow velocity, the direction of the flow velocity relative to the vein is not following the vein angle at the inlet, there are losses. And this will happen if the compressor does not work at its design condition. So, therefore, of design conditions, the incident losses will take place when the flow cannot glide the vein both at its inlet and outlet, that is the relative velocity angle differs from that of the vein angles. Another is the clearance or leakage losses, which takes place because of the clearance between the impeller eye shaft and the casing of the compressor. Okay. Or the impeller eye and the casing, impeller eye tip and the casing. These are typical mechanical things. We can reduce that by proper sealing. But when the impeller eye tip diameter is very large to accommodate more mass flow rate, this sealing becomes a problem. So, we can reduce that by putting glands, providing glands to reduce the leakage between the clearance between the shaft and the casing. So, these are all clearance and leakage loss, but this clearance and leakage loss is comparatively very less as compared to frictional loss and incident loss. Now, if you draw a figure of losses versus mass flow, this is mass flow, then you will see this type of figure. Frictional losses is like that, it always increases with the mass flow like this. Frictional losses with mass flow, it is like this. This is 0 when there is no mass flow, but incident losses gives a picture like this. This is minimum at the design point. This is the design point, and of design point take may be there even at low mass flow and high mass flow. These are off design point where in both the directions this increases. So, if you add these two, the total losses take place. Total losses takes this shape, total losses. Okay. So, these three are the important losses, but this is not as important, this is relatively less as compared to the friction losses and the incident losses. Okay. I think today I will end here and we will discuss the compressor characteristics in the next class. Thank you.